A factory manufactures two kinds of ice skates, racing skates and figure skates. The racing skates require 6 work hours in the fabrication department, whereas figure skates require 4 work hours there. Racing skates require 1 work hour in the finishing department, whereas the figure skates require 2 work hours there. The fabrication department has available at most 120 work hours per day, and the finishing department has no more than 40 work hours per day available. If the profit on each racing skate is $10 and the profit on each figure skate is $12, how many of each skate should be manufactured each day to maximize profit? We'll assume that all skates that are made are sold. We'll use linear programming to set this up. We start by labeling the unknowns. Since we have two knowns, let's use x and y. The first unknown is the number of racing skates that are needed. And then the second is the number of figure skates. Next, we create the objective function. That is the thing we're trying to maximize or minimize. In this case, we're trying to maximize profit. So z, evaluated at x and y, is going to have something to do with the profit on the skates. So we need to look for everything that has something to do with money. We have racing skates for $10, so that's 10x plus the profit on figure skates is $12. So we'll think of that as 12y. Next, we'll set up the constraints. The first two are somewhat obvious. X and y have to be positive. So we're going to be restricted to quadrant 1. The next two constraints involve the fabrication department and the finishing department. So let's start with the fabrication. Everything involving fabrication. We see that racing skates require 6 work hours in the fabrication department. So we can think of that as 6 times the number of racing skates. And then the figure skates require 4 work hours there. So we'll think of that as 4y. Next, the fabrication department has at most 120 work hours. So we can't go over 120 for the fabrication. Next, we'll go through the finishing and figure out everything to do with finishing. The racing skates require 1 work hour in the finishing department, so that's just 1x or x. The figure skates require 2 work hours there. We can think of that as 2y. And then we have no more than 40 hours in the finishing department, so the total can be less than or equal to 40 work hours. The next thing we'll do is sketch a graph. So we are restricted to quadrant 1. And to sketch these lines, we have options. I'm going to choose to use intercepts. I think that's easier in these types of problems. So the first one, we'll set it equal to 120, change it to an equation. And recall to find the x-intercepts, we make y 0. So if y goes to 0, we have 6x equals 120 or x equals 20. That coordinate would be 20, 0. And then to find the y-intercept, we make x 0, so this term goes to 0, leaving us with 4y equals 120 and y equals 30. So our coordinate is 0, 30. The other equation we have is x plus 2y equals 40. Again, using intercepts. To find the x-intercept, we make y 0, this term goes away, and we're left with x equals 40, or the coordinate 40, 0. And to find the y-intercept, we make x 0, so this term goes away, leaving us with 2y equals 40. divide by 2, and y equals 20. The coordinate would then be 0, 20. Now we can use these to help us sketch these two lines. I'm going to increment my tick marks by 5s, so 5, 10, 15, 20, 25, 30, 35, 40, 5, 10, 15, 20, 25, 30. And let's see, the red intercepts, the x-intercept was 20 and the y was 30. Draw that line. And then for the green, we had an x-intercept of 40 and a y-intercept of 20. Next, keep in mind that these are actually inequalities on the constraints, so we need to do some shading. We can pick any test point we want. The easiest to pick is the origin, 0, 0. If we plug 0, 0 into this red inequality, we get a true statement, which means shade below the red line. Same thing with green. Pick 0, 0, plug it in, we get a true statement, which means shade below the green. So our region that we're interested in is everything that's below green and red, but we also want to stay restricted to quadrant 1. Again, negative values don't make any sense. From here, we want to plug each of the vertices of that shaded region into the original objective function. So we have this point, which is 0, 20. We have this point of intersection, which we don't know yet. And we have this point, which is 20, 0. Technically, we also have 0, 0, but if we make 0 racing skates and 0 figure skates, we'll have 0 profit. So we're going to ignore that one. Let's next find this coordinate. Notice that it is the intersection of these two lines. So to find that, we can solve the system. I'm going to choose to use a matrix. We have a number of options to use, but a matrix is the easiest. We'll plug those into the augmented matrix and reduce it to get that intersection. So in the calculator, we go to second matrix, go right to edit. This is a 2 by 3. Then we'll enter in those values. 6, 4, 120, 1, 2, and 40. Exit the matrix by hitting second quit. Now second matrix, we'll go right to math, and we're going to scroll until we find RREF. Tell the calculator what to reduce. So second matrix, hit enter, then close the parenthesis, enter one last time, and we get a reduced matrix. 1, 0, 10, and 0, 1, 15. That means this coordinate is 10, 15. Next, we want to plug those 3 vertices into the objective function that we found earlier. So z evaluated at 0, 20. That is 10 times 0 plus 12 times 20. That will give us $240. Next, we'll plug in the intersection that we found, z evaluated at 10, 15. 10 times 10 plus 12 times 15. 10 times 10 plus 12 times 15. That gives us 280. And finally, z evaluated at 20, 0. That is 10 times 20 plus 12 times 0. This will give us $200. In all three cases, there is a profit, but our goal here is to make the maximum profit, and that occurs when we make 10x, that is racing skates, and 15y, or figure skates, for a profit of $280.